In this lesson, robots move beyond simple commands. Cameras collect visual data, AI looks for patterns and objects, and code turns those results into action. We'll connect seeing, deciding, and doing through hands-on Raspberry Pi projects. So far, you've built the pieces that make robots work: controllers, sensors, motors, wireless control, IoT projects, and camera hardware. Each module added another capability, from reacting to the world to being controlled remotely. Now we'll connect those skills to AI vision, so a robot can do more than sense. It can recognize what it sees. In robotics, AI acts as the decision-making layer between sensing and action. A camera or sensor collects raw information, such as an image, a sound, or the shape of an object. The AI model looks for patterns it has learned from examples. It might classify a face, detect an apple, or decide whether a path is clear. Then the robot uses that result to act. The key point is this: AI is not awareness or life. It is math, data, and programmed goals helping the robot respond more flexibly. Robots can make decisions in two very different ways. With rule-based control, the programmer writes the exact condition and the exact action. If the distance is less than 20 centimeters, stop. That works well for clean sensor readings like distance, light, or a button press. Eye recognition is different. Instead of one simple number, the robot may receive a messy camera image. A detection model searches for learned patterns, such as a face, a person, or an object. Rules are precise. AI helps when the world is visually complicated. To an AI vision system, an image begins as a grid of pixels, tiny squares with color values. The system searches those pixels for clues, such as edges, repeated colors, simple shapes, and textures. No single clue proves what the image is. But when many clues appear together, the system can make a likely prediction, such as, "This looks like a face." This is challenging because the same face can change with lighting, distance, angle, or background. Classification means a vision system chooses the label that best matches what it sees. An image might be labeled person, cat, bottle, ball, or unknown. The model often reports confidence, such as 90% ball, which means ball is its strongest guess. But confidence is not a guarantee. When the situation is uncertain, a robot should slow down, ask for help, or choose the safest action. Classification tells a robot what an image contains. Object detection adds the missing piece, where each object is. The system finds individual items, draws a bounding box around each one, and attaches a label with a confidence score. That location information makes vision useful for action, such as moving toward an object, avoiding it, picking it up, or pointing it out. Face detection and face recognition sound similar, but they answer different questions. Detection asks, "Is there a face here?" It can draw a box around a face and react without knowing who the person is. That is usually enough for projects like a camera that triggers a photo booth or a robot that turns toward people. Recognition goes further and asks, "Whose face is this?" Because that connects images to identity, it requires consent, security, and a much stronger reason to use it. Think of computer vision as a pipeline, not a single magic step. First, the camera captures raw pixels from the world. The Raspberry Pi then prepares the image by adjusting size, color, or contrast, so the model can use it reliably. Next, the AI model detects or classifies what matters, such as a box, line, face, or obstacle. Finally, the robot turns that result into a decision: move, stop, sort, pick up, or avoid. When something fails, debug one stage at a time. Robot vision starts with frames, single images captured many times per second. The Raspberry Pi analyzes those frames to notice motion, recognize faces, or find objects like an apple. Higher resolution gives more detail but takes more time to process. Lower resolution is faster, but may miss small features. Lighting and camera angle matter just as much, because poor conditions can confuse detection. A good robot balances quality and speed, so it can understand what it sees and still react quickly. Before an image reaches the detection algorithm, it is usually cleaned up and simplified. Resizing reduces the amount of data, which is important on a Raspberry Pi. Brightness adjustment helps details stay visible when lighting is too dark or too bright. Noise reduction removes random speckles and distractions that could confuse the model. Color conversion, such as changing RGB to grayscale, can focus the analysis on shape and contrast instead of full color detail. The goal is not to make the picture prettier. It is to make the important patterns easier for software to recognize. Detection by itself does not make a robot intelligent. It becomes useful when the result is turned into a rule the robot can act on. The label tells what was found, the confidence tells how sure the model is, and the position helps choose where to move. For example, if a person is detected with high confidence, the safest action may be to stop. If a ball is detected, the robot might turn or follow. Always design action rules so safety comes before speed, excitement, or clever behavior. AI learns from examples, not from true understanding. Training data shows the model patterns, such as what cats, cups, or balls usually look like. Testing asks a harder question. Can it recognize new examples it has never seen before? Sometimes it can. Sometimes it fails because the image is blurry, the lighting is poor, the angle is unusual, or the training set did not include enough similar cases. That is why robotics should never rely on AI alone. Good designs include backup rules, confidence checks, and safe stop options. Camera vision gives robots useful awareness, but it also creates responsibility. Before recording anyone, ask clear permission and explain how the images will be used. Collect only the data you truly need, store it carefully, and delete it when the project is finished. Test your model with varied lighting, backgrounds, and different people, so it does not work well for only one group. Finally, plan for uncertainty. If the AI is unsure, the robot should slow down, stop, or ask for help instead of guessing. AI gives robots a way to recognize patterns in messy inputs like images, while rules keep their actions safe and predictable. The vision pipeline is now clear: capture, process, detect, decide, and act. Next, you'll turn that pipeline into real Raspberry Pi builds, starting with face and object detection, then an AI vision rover.